Okay, thank you, Jerzy, for the introduction. So today I want to treat in quite a bit of detail to confirm the flat case, so Minkowski space. And the idea is that on the way, I will try to introduce and to highlight the essential aspects, which are not so much specific to Minkowski space, but that we generalized in the general case of asymptotically flat space. So, I mean, really, I'm going to introduce the main definitions along the way and tell you that these will are the definition in the general case. Before I start, I wanted to say a few things about the last lecture that I didn't have time to say. So first thing, there are these invariants, which are very classical whenever we are talking about null geodesic congruence. So I thought I should tell you, write somewhere what they are. The expansion, the shear is going to be very important. And it's written in the lecture notes that should be on the website, or you would get at a point or another. And you can check for yourself. This is a small exercise that these guys, they do not depend on the choice of M and M bar. So yeah, another thing. So yesterday I had a nice question. Someone asked me, why is this term 0 in the computation? And my answer was, it's due to Bianchi identity. And this was not correct. So Bianchi identity is very important for reducing all the components of the Weil tensor to just these 5 Newman-Penrose coefficients. But the reason why this object is 0 is really because this is computing a trace of the Weil tensor, which is 0. So this is the correct answer. So I just wanted to highlight this, unless you ask yourself this. Okay, so with this first remark, let's play a little bit with Minkowski space now. So you want to start with, so the essential, there are several ways of introducing the conformal compactification of Minkowski space. I'm going to do it in the most pedestrian way, by changing coordinates, because this will be, this is one way of doing it, which is very practical. So we start with Minkowski. So I'm going to write the line element with a tilde. So the physical metric is going to have a tilde everywhere on it. Dt squared plus r squared plus r squared d sigma squared. This object is the round metric. So this is the metric on the two-sphere written in stereographic coordinates. And of course, you have to remember, it's important to keep in mind which is the set. So T and R and little r, they are real numbers, but R, it has to be strictly bigger than 0. There is some sort of coordinate singularity happening at r equals 0 in this coordinate system. Okay. So then we change coordinates. So proposition. What? Plus. Maybe I got confused with my number. Yeah, you're right. Yeah, thank you. Okay. So we change coordinates. So first step is to go to advanced and retarded time. So we pose u is t minus r, advanced retarded time, and v equal t plus r, which means that u and V, they belong to R, but the difference, V minus U, which is 2 times the radius, must be positive. And then the matrix is just simple, is of this form, minus du dv plus 1/4 V minus U squared T sigma squared. So this is a type of doubly null coordinates that Sabrina was asking for yesterday. It's doubly null because both du and dv are null. There are no squared term. So already with this is very good, but we want to compactify to infinity, so we want to change to big U. So which one? So you introduce big U, which is such that tangent of big U equal little u, and big V such that the tangent of big V is little v. And now U and V, they belong to minus pi over 2 to pi over 2. And we must have, because of this condition, we must have V minus U positive. Let me take another blackboard to write the final metric, because this is the most important part. So what do we get? From this coordinate transformation, we get the following thing. We have 1 over 4 cos squared big U cos squared V times minus 4. Well, hopefully the numbers are right, but dv dv plus sine squared V minus U d sigma squared. So what's the remark here is that now, so infinity was, so we want to compactify infinity. So, okay, I should explicitly say, even though I'm sure you've seen this idea a few times, so there should be no surprise. The idea of conformal compactification is that we want to bring the infinity of Minkowski space at finite distance at the boundary at infinity, such that the Minkowski space together with the boundary added at infinity is compact. The boundary is going to be at infinity, so at r going to infinity, but r going to infinity is also u and v going to infinity. So this is going to have something to do with big U and v going to minus pi over 2 or pi over 2. So these guys will blow up in these situations, but this one will not. So what we see is that up to this scale, the overall scale in front, which I and many people are calling the conformal scale. Well, up to this scale, Minkowski space, the metric is finite. So this metric, which I'm going to call the unphysical metric. It's unphysical because the physical metric is Einstein. I rescale it. I get something which is not an Einstein metric, but which is going to be finite at infinity. So the unphysical metric, and which is I'm going to write as ds squared without any tilde. So we have, so this is equal 1 omega squared ds tilde, d squared tilde, and omega, just for me to remember, is 2 cos u cosinus v. So this object is the conformal scale. Yes. So let's draw the diagram. So we have u and v coordinates. So we are going to have a diamond. So this is, I'm sure you've all seen many times this conformal picture from Minkowski space. So yeah, the way I define it is that in green, I'm going to draw surfaces of constant v. So this is, so green is v equal constant. And I have here increasing v. And it's going to v equal minus pi over 2 to here v equal pi over 2. And on the other side, I have constant u surfaces. And it's going, increasing u is going in this direction. And it goes from u equal minus p over 2 to here u equal pi over 2. You see the fact that it's only half of a square and not the full square is really due to this constraint here that v should be bigger than u. But of course, here it's a two-dimensional picture. Minkowski space is four-dimensional. And what has been suppressed here is the spherical type of coordinates. So you should keep in mind that you have spherical symmetries here, and that each of the points on these diagrams are spheres. Right? Okay, so now let's discuss. Okay, and this, now I'm going to have a bunch of remarks about what is going on here. So again, why, what is this diagram? This diagram is about where are these functions defined. Minkowski space itself, so this metric, let me write this down explicitly. So Minkowski space itself is not defined on the wedge, it's only defined in the interior. Here it is. So what do I to say? Yeah, so I'm going to have a bunch of crucial remarks about this model, what we should remember and keep in mind for generalizations. Okay, so the idea, this picture is really telling you that we are adding a boundary at infinity. So the physical metric, so Minkowski space. So the physical metric, which I'm always going to write with tildes. So d tildes squared equals g tildes mu nu dx mu dx nu is only defined in the interior, and interior here equal Minkowski. But the unphysical metric which I'm going to write without any tildes, which is this object. So this object is perfectly fine. You can take v and u being the boundary value, and it's fine. And I'm going to write this object without any tildes. We don't say, yeah, extends everywhere. Okay, so Minkowski space itself diverges as you reach the boundary, which better be because the boundary is at infinity, so the distance needs to diverge. But the conformal metric, meaning the metric seen understood up to scale, is finite. Yeah, so you have, this is the notion of conformal compactification. Okay, so let's discuss what's happening. Compactification. So now, what's interesting is what is happening. So what can we say exactly? Which is, yeah, let's discuss. So before, let's discuss what's the properties of the boundary now. So you have a bunch of points which are a bit singular, which let me prove in orange, say, which are past time like infinity, which we're going to write as I minus, space like infinity, I0, and future time like infinity. They are a bit singular. Why? Well, okay, so the first thing you have to realize is that the boundary itself, it's a bit tricky. The boundary itself is not a manifold, precisely because these points are somewhat singular. So let's look at what, so yeah, let me write this down because it's important to keep in mind. The boundary is not a manifold, and we'll see this. So it's different from AGS in this sense, precisely because of this strange I plus I0, I minus. So rather, it is made up of 5 pieces, which are manifold. Okay, so you have, as I discussed, we have so future time like infinity, I plus, which is given by u equal pi over 2 and v equal pi over 2. Should easily see it on the diagram. So past time like infinity, time minus, which is what? Yeah, u equal minus pi over 2, v equal minus pi over 2, and space like infinity. U equal minus pi over 2, v equal pi over 2. So the main thing to see here is what is the induced metric doing at this point? The induced metric is, so of course, by this I mean take the unphysical metric, it extends everywhere, you take this metric and you restrict it to these singular points, and these points, this is 0 because we are just restricting it at v and u equal constant, but also this is going to be 0 because we are at this boundary. So the unphysical metric ds squared restricted to this iota point is identically 0. So there is just, this metric is just completely 0 everywhere on this point. So these points, they have absolutely no extension. So that's why we say they are points. If you want to embed this inside the genuine manifold, this I0, I plus, I minus, they have to have 0 extension, and therefore they are points. So if you want to think this as manifold, they are 0-dimensional manifolds. Okay. Now, of course, the part which is really interesting is cry. So the extended boundary.
Isn't this just the case that we're using coordinate system that is not adapted to these 3 points, and that we could use a different coordinates to actually resolve this?
Yeah, so this is why this presentation is a bit unsatisfactory, because this way of presenting the things make it look like it's all about coordinates, okay? So the answer is no. It's a feature of the images. So okay, another way of presenting this story that perhaps would be more satisfactory is you want to look for an embedding of Minkowski space into a conformal into a compact manifold, which is a conformal embedding, and then you need to convince yourself that it's that you cannot do this in a way which extends this point. One way to, yeah, I guess another way of saying this is that if you want the conformal group to act on Minkowski space, so if you want this to be a conformal embedding, you better have the conformal group acting on Minkowski space, and then it's only going to produce one conformal embeddings, which is start with the conformal sphere. So yeah, maybe. I'm not going to discuss this, but that would be sort of another way of presenting the lectures. But one way of doing this would be start with the conformal sphere in 4 dimensions, on which the conformal group acts act transitively, so the homogeneous space for the conformal group, and then choose the inside. So this would be what essentially a version of what Tim presented. You start with the conformal group, start with conformally compactified Minkowski space, and then reduce. And you would see that there is no way around this point being, this object being points. Of course, here it looks like I'm just changing coordinates, so it's hiding a bit that. But no, there is no way of, in the sense of conformal compactification, there is no way of having something which is other than points for this time-like, space-like infinities. Maybe but there are ways of resolving these infinities, but not using conformal compactification. For example, if you use projective compactification, then this would go another way around. You would have extended space-like and time-like infinities, and then scry would be crunched. Okay, so it's a feature of conformal compactification that these objects are somewhat singular. But of course, we care about conformal compactification because we care about gravitational waves and fluxes, which are massless field, and they are going to follow null geodesics, and they have nice feature in conformal feature. And as Tim explained this morning, a lot of these these things, they are conformally invariant and everything. So, okay, but I want to, that's one way of doing the presenting the subject. The reason why I'm doing this is that then it's very explicit. We have coordinates, and at the end of the day, this is what we will be using. Okay. Yeah, I was about to discuss scry, so let's discuss a bit of on the geometry on scry. So future null infinity. So which I'm going to note scry plus. Now is u is allowed to have some extension, minus pi over 2. Pi over 2, and v is in the future, pi over 2. There would be past null infinity as well, so this is the other part of it, pi minus, where it would go the other way around, so u is fixed to be minus pi over 2, but v can go to some extension. So the main feature is, so the first thing is that these are manifold. These are 3D manifolds with coordinates U Z D bar. You see what's a bit tricky is that if this I plus, I0, I minus were really corners, then there should be two-dimensional manifold boundary for this one. And they are not really because, as we see, the geometry is very degenerate. So it's not a good idea of thinking of this overall boundary as being a manifold of itself. Scry itself is manifold, and you should really think that you're taking out this point and forgetting about the singular point, yes?
Sorry, what if you include the sine squared v minus u in the conformal rescaling? So you have one over sine squared v minus u in the first term, but having picked values of u and v, you don't see the first term, you just evaluate the S2 metric anywhere on the...
So if you take this one out here,
Yeah.
well, then this one would diverge, so that would not be very satisfactory. You would have 1 over sine squared, which goes to 0 at this corner, so that would not be very nice.
That's true, but also the du and the dv are also 0. Right? The biggest point.
Right. So I mean, yeah, your metric would be ill-defined, so you don't want to do this. So I mean, again, the problem with this way of presenting the thing is that depending on what is satisfied, there are many type of answers depending on what is satisfactory for you as a presentation or not. So if you want, okay, what's the feature here really is that this is genuinely defined everywhere on this triangle. This metric makes sense on the whole of the triangle. As a so the conformal geometry really extends everywhere. That's the feature of this conformal compactification. So, and you don't want to spoil this. You want the conformal geometry to be genuinely well defined everywhere. But the price to pay is that the conformal geometry is 0 on this singular point. So there is no extension for these points. Yeah, please.
Because, well, this construction is seen, it's like well known. But
Yeah.
I was wondering if this feature, for example, is something universal of any compactification on Minkowski space. Is it possible to prove that any compactification will end up?
It's a conformal compactification. So again, this is very important. All of this, they are features of a conformal compactification. So it's universal in the following sense. You want to start with Minkowski space. The Poincare group acts on Minkowski space. You want to embed the Poincare group inside the conformal group and look for a bigger space on which the conformal group would act. This is the only construction that would do this.
Yeah, I was
You
wondering
see?
if it is possible to prove this
Yeah.
statement, or
Yeah. Again, this would be the sort of proofs that you would have to do. Like, start with, or maybe, yeah. You start with the Poincare group. You're trying to embed it inside the conformal group and look for a manifold in which the conformal group would act, such that there is Minkowski space inside this manifold, and you would find that there is a unique one because this, yeah. So that would be the way to do that.
does this uniquely fix also the conformal factor and so on, or there is some freedom?
No, okay, yeah, I'm going to that. No, precisely, there is an ambiguity. I will discuss that. I will discuss very soon where is the ambiguity. Yeah. But again, it's not the unique compactifications. There are other ways of compactifying Minkowski space. For example, projective compactification, which has completely different features. Okay, so what we are seeing here is a feature of a conformal compactification. Conformal compactifications means that we are looking for a metric which is finite up to scale. So you start with Minkowski. The only things that you're allowed to do is rescale that metric. That's the only game that you're allowed to play. And you look for a way of having a compact metric. Okay. Yeah, for Minkowski, it's unique. I should say, when we come to the general definition, I think there is no theorem telling you that a space-time which is asymptotically flat has a unique conformal compactification. I think in this case, this is not known. So here, it's unique because it's Minkowski, and you have this group of symmetry acting on it, so there is not much that you can do for the conformal compactification. Yeah. Okay, so it's a manifold. We have coordinates u, z, z bar, and now if you restrict the metric on this, well, it's important. I'm going to write it. It's a null metric, so because you can check that. So coordinates would be u, z, z bar, but it's u plus cosinus squared of u for dz bar And so what the feature here are is that this is 0, so it's important. It means that, so the induced metric on this boundary is degenerate. So the metric is degenerate. So it's a null boundary. It's very different from ADS. So also this radius is interesting because it's really, so this is like so this is the round sphere metric, and this is the radius of the round sphere metric. So what this is telling you is that the metric as u goes to minus pi over 2 or pi over 2, as u goes to plus or minus pi over 2, the metric, the radius goes to 0. So we find again this feature that asymptotically the metric. So I think the picture that you should really have in mind for scry, I think the right picture is something like this, is really that you have some sort of object like that. So you have spheres which are embedded into scry. So maybe I should write them in blue because it's really these constant u terms. So you have spheres. So these are u equal constant. But asymptotically, the sphere, it shrinks. And here you have the radius is shrinks. And here you have really the radius of the sphere goes to 0. So here r goes to 0. So you see, that's why it's, you should not think, that's why I wanted to say, you should not think of this as being a manifold. It's some sort of a squeezed object. Okay. What else do I want to say? That was it for the boundary. Any other question about this? Again. Now, most important remark. So here I'm going to write a bunch of facts about the construction in such a way that, in fact, this is going to be the definition of a generic asymptotically flat spacetime. So, here, so I note with tildes the Minkowski space metric. So first of all, what did we find? We find that there exists another manifold M without tilde, which is in fact M tilde together with scry plus and scry minus. And I don't want to add I plus 0 because this guy now is a manifold with boundary. And the boundary is scry plus, scry minus. We also find that there exists a function omega and another metric g mu nu without tilde, scalar field and metric on M, so on the wall of the manifold, such that G tilde mu nu equal 1 over omega squared G mu nu on M tilde. So we found bigger manifold with boundary. The boundary we call scry. It has two components. There exists a scalar field and G mu nu. These guys, they are defined on M, so on the manifold with boundary, such that when we take the ratio of the two, well, the ratio of the two cannot be defined on the boundary because this is blowing up, but this is defined on the interior. The interior is Minkowski space, and we recover the physical metric. Yes. And it's important also aspect of this is that at scry, omega equals 0, but d mu omega is not 0. So we say that omega is boundary defining. So the fact that it's important that the first derivative of omega is non-zero. Otherwise, you would have no normals. So that would be annoying. For example, you can check that, in fact, this is not the case. At this point, I plus, I minus, this goes to 0. And this is one of the problems with this object. Yeah, let me, I like this because that's the main. So this is going to be the definition of an asymptotically flat manifold. It should satisfy these axioms here. Okay. So this was, if you want, this was really, I think, Penrose's genius to realize that you can take this feature from Minkowski space, take them very seriously, take it as a definition for any asymptotically simple, asymptotically flat manifold, and this would give you nice features and nice results. These are nice space-time to consider, the one which are satisfying these axioms. Is there any question about this definition and everything? No? Okay, and indeed, there are some ambiguity about what we mean in this definition. So where is the ambiguity? Yeah, please. Yeah, you don't want to do this here. So maybe what you want to say is that what's tricky is that this manifold here is not compact. This is one of the subtlety. So this is why in the literature, and Penrose did not call it an asymptotically compact, like asymptotically conformal compactification, or it's called asymptotically simple spacetime. Is that really this is a conformal compactification of Minkowski space because you have these nice points which are well behaved and such that really Minkowski space is conformally compactified. But in general, you would not be able to do this with an asymptotically simple spacetime. What you would get is nice boundaries which are which are the scries, but this manifold is not compact. You're missing points at space-like and time-like infinity because they are very badly behaved in general. So you cannot add them as boundary of your asymptotically simple spacetime.
So you just remove them from your manifold, I0?
Yeah, if you want. So from this perspective here, I just forget about them. What I want to call M is just take Minkowski space, you add the scry, but you don't care about I plus and I minus. And generically, this is the picture you should have in mind when you have an asymptotically simple spacetime, is that it's like Minkowski space where you do not have this point because here, only in Minkowski space, these points are going to be well behaved. Okay? In asymptotically simple spacetime, they are going to be very bad generically. Yes.
So I wanted to ask: is it necessarily obvious that this is like the uniquely good way to define asymptotically flat?
No. I mean, you see, that's what I tried to say last time. That there was, what is a good definition for an asymptotic flat spacetime is absolutely not obvious. That's why it was a long-standing question. And and what is a good definition has to do with what kind of answer you want to have. And clearly, the answer was you want a definition such that allows you to sort of make sense to presence of gravitational waves invariantly. That was the big question. There were different ideas that I tried to describe last time. Along this idea, you take no geodesic congruence, you go to infinity, you try to impose some follow-ups on the Wild tensor, etc., etc. very close related ideas, which is a great idea. Was this idea by BMS introducing some particular coordinate system and solving order by order? I will come to this. But turns out, and as you know, it's just sort of what people do with this consensus. So when I'm going to try to convince you that this is a good definition, turns out that this definition, which is very simple, it's a very simple definition, turns out that it encodes a lot of the information that you care about. And for example, as hopefully I try to explain, this implies Sachs spilling, for example. It's not obvious at all when you look at it, but this implies Sachs spilling, this property that I told you yesterday. It's a bit of a magic here, please.
Okay, so actually, in that topic, so since we're being pedantic, what sort of regularity conditions?
Right. Okay, so it's another very good question. It was a very good question. That was a question that was standing for a long time. Naively, and this was Penrose's suggestion, you would like this to be C infinity. You read a genuine, smooth, conformal compactification. And then, if the question is, does it make sense? Another question related to your question is, does it exist? This is a definition. Is there any good solution for this? And this was a long-standing question. Can you produce any solutions? And then mathematical physicists, they work hard to produce solutions. What you need to do is really solve Einstein's equation and control the asymptotics. And they managed to produce, now we know that there are many solutions. So different results, you have different results. One result is Christodoulou-Kleinerman.
But they're not smooth.
Precisely. So this is, they are producing a lot of solutions, but generically they are not smooth. But now you have another result. It's a family of results starting with, I think, Friedrich, up to Kruschel and Delay solutions. And these solutions, they are smooth. So there exist an infinite and very large class of solutions which are these properties, and they are well defined everywhere asymptotically. So for everyone, this question of smoothness and non-smoothness is really about, if you care about your BMS expansions, whether or not you want to introduce logs in this expansion. It's a very natural question. You solve order by order, and then you realize that you could also have solved the equation order by introducing logs, and then this logs has to do with the fact whether or not you want your boundary to be differentiable. And this was an outstanding question, whether there exists any solution without any logs in the asymptotic expansion. They are many now. And then the question is whether or not they are, to which extent what's the physics of this log? I think that's a question that many people are asking themselves today. This is not very clear what the answer is. What is the physics of this logs, this lack of differentiability that can appear? Is there some physical relevance for this or not? And I think probably it depends what type of problem you want to solve. Yeah, please.
So if you have any Cauchy slice in the finite time, then the Cauchy slice doesn't have a boundary because I0 is not included.
Yeah.
Then you cannot, then how do you, if you have a gauge theory that localizes into the boundary of the Cauchy slice, meaning whose action localizes to the boundary of the Cauchy slice, then how do you write down the action if you don't have the boundary?
Well, yeah, I mean, that's, if you want, that's a problem with this way of thinking, yeah. I mean.
So to clarify, you have do you have I0 in your manifold, or do you remove that?
In this definition, you don't ask anything specific about the behavior at I0 at I plus or minus. It's not part of the definition. So then, yeah, perhaps you want to say that in this sense is not a good definition. It's another question. So, but no, you don't. Here in this definition, you're not requiring anything about the behavior at I0. Yeah, at I0.
Okay, but your manifold still have I0. You just don't impose any constraint or anything on I0. But your manifold still have I0.
I don't know. Yeah, I don't know what you. I mean, no, in this definition, you don't have I0 if you want. No, you don't. Then you could ask for more. You could ask, actually, I want a manifold where square plus and square minus, they meet in a point, and I want to ask for this or this behavior at I0. That would be extra requirements. But naively here, at this level, you don't have this particular point. Okay? Okay. So okay, thanks a lot for all these good questions. I think they are well, they are all the questions that I have to be asked in this context. Okay, yeah, so what's important is that it's really conformal, so there is nothing unique. I think this is good to keep this in mind. There is nothing unique. About the pair omega g mu nu. We could take omega hat equal f of x omega and f and g at mu nu equal f squared of x g mu nu. And this would work just as well because the physical metric is the same. So really what we have conformal fields or conformal densities. Yeah, conformal fields. So omega, so this equivalence class, right? G mu nu is equivalent to f omega f squared g mu nu. Yes, and all of this to discuss. Yeah, I'm going very slow. So in particular, at the boundary, yeah, let me write this here. So in particular, the normal to scry is not unique. So the normal to scry is this object. G, so n is G mu nu, d nu omega, G over Gx mu scry equal cos of u G over du. And it's also, this guy is defined up to f squared, this guy also. So this is the metric. Yeah, so we have, let me keep the metric here. Let me erase that one. So the normal is only defined up to, so I want to keep this because I like, so I'm going to call this H. This is the induced metric. And so we really have these equivalence classes of, so little a, so xa, they are u and z bar. Yeah. So we really have this equivalence class at scry, and this is what in the literature this object is called universal structure of scry, or also in some part of the literature you find the term Carolian structure of scry. Okay, so this is something which is here at Scry, just the fact that the metric is degenerate, but it's also a conformal metric, and you have vector field in the degenerate direction. It's in du direction. And it's also, it has a particular way of transforming under conformal metric. So because it transforms, in fact, we could have chosen here, it's a function times the sphere. So we could choose this function to get rid of this number in front. So we are going to do this, and this would be BMS coordinates. That's where I will stop, I think. So let's finish with BMS coordinates. Yeah. So we start again from Minkowski. This time we keep again u, t minus r, but keep omega equal r minus 1, and we obtain the following conformal compactification. So it's minus du squared plus 2gr. So this is, again, the unphysical metric. And this is the conformal scale. But now, the induced metric at Scry is really just genuinely the sphere metric. Yeah, so something important here is that Scry minus is not covered here. But it turns out that this was the right type of coordinates that you want to generalize in the asymptotically flat case. And also in this form, this is very clearly, it really means that these BMS coordinate systems are related to a null geodesic concurrence. And this is the same type of expansion that I wrote down yesterday. So, yeah, I think that's about what I wanted to say today. Is there any question on this? So, yeah, please.
Because in correspondence we care about the behavior at the boundary, right?
Mm-hmm.
So, is there some clear clarification of how we expect compactification of spacetime to behave at asymptotics to make a well-defined dual? So, so if you were to try to cook up the CFT at boundary of some spacetime, right? Do we approach it via compactifications, or we do some more exotic procedure to? What I'm asking is, like, under which condition can we claim that we have well-defined manifold on the boundary where we could construct the EFT basically? Is it connected with the
So you see this picture. Okay, maybe there are a few things I should say. So you see this picture. One reason why, I mean, there are many reasons why it's natural. First, for one thing, so I wanted to say that this is the exact analog of your Pfefferman-Graham expansion, or what you would do in the usual ADS-CFT. It's exact similar constructions. By the way, these ideas of Penrose of doing the conformal compactification dates far before even Pfefferman and Graham. Yeah. This is really, I mean, and even this idea, I mean, of course, even this idea, they don't think. Well, you see, what's brilliant about this definition is that this definition by itself has brilliant implication that, for example, it implies Sachs peelings. It has a lot of properties that amazingly just follow from this simple definition. Of course, the definition by itself is not, it's a very simple definition. So what I want to say is that, yes, what's good about this is that it's precisely the same as in the ADS-CFT construction, conformal compactification. Actually, you can really, at least locally, you can really take ADS and take the lambda going to 0 limit. It's a subtle limit, so you have to be a bit careful about the way you're doing it, but you need to make some choice. Because you see, what's going to be the problem precisely of this point? Like ADS has a nice boundary, which has no preferred point. So if you want to take some limits, you see that there will be something preferred after the limits. Some points will be singular, will be different. And also, this cry has a preferred direction. So if you want to take a limit, you should take the limit in such a way that after you've taken this lambda going to 0 limit, there is a preferred direction along your manifold. Okay? So the only way to do this is that you need to start with ADS, choose some direction along the boundary, and then degenerate the metric in that particular direction to obtain scry. So there are some choices involved in how you want to take the limit. You can't just take lambda to 0 limit and expect to have something finite. You need to make a choice, choose some time on your boundary of ADS, and then degenerate into that direction. Doing so would give you, so what's interesting, and this is what I was naming this, is that from the perspective of the boundary, there is a classical way of degenerating a metric, which is the Galilean limit. You start with Minkowski space, you degenerate the metric in one direction, and you get your usual Galilean geometry, because Galilean geometry is degenerate because you have a preferred time. So if you have a preferred time, this means that you have slices of space, and along this matrix, well, the metric must have some very specific behavior. So the metric degenerates with preferred slices of space. Here, the same thing is happening, but it's not the same as the opposite. So instead of degenerating your metric to get nice slices of space, you're degenerating the metric in such a way that you have a slicing by lines. And this type of limit is in the limit called Carolean limit. So instead of taking the speed of light going to infinity, you're taking the speed of light going to 0, and you have this different way of taking the limit of the boundary geometry. And there is a very precise sense in which once you've made this choice of choosing a time at the boundary of ADS, you can degenerate. Taking lambda going to 0 limit is the same as taking this time going to 0 on the boundary. So you're really taking a Carolean limit of the boundary geometry as you're taking lambda going to 0 limit. So in this sense, it seems like a natural definition because this is really what you would obtain as a limit of your usual conformal compactification in ADS. So, I mean, if this is the right idea, I think this is seems a very good starting point, and I think that's everybody's perspective. Of course, you could imagine, perhaps even like, you could imagine there's really, scry. So this is, from this perspective, you would tend to think that the right boundary for your holographic theory is scry, but maybe really we should just really care about the celestial sphere, and celestial holography is more going perhaps toward the idea that celestial sphere itself, so just the cuts are very important. Maybe, or you could even imagine that maybe it's a wrong idea. Maybe you need to go to I plus or I0, and there is more structure there. So you could, but again, naively, taking the lambda going to 0 limit of your usual ADS-CFT would produce this sort of things. Is there any other question on this? Okay, not well. Okay, so thank you for today.